Welcome to Networks Professionals.
So, AI is everywhere, right? We hear about it constantly. But have you ever really stopped to wonder what's actually going on inside its head? How does a machine really learn to see or to write or to create something new? Well, today, we're going to unbox all of that. We're going to build an artificial brain right from the ground up. Okay, let's just push aside all the sci-fi stuff for a minute and ask a really basic question. What if you could actually design and build a thinking machine piece by piece? Well, that's the exact question that the pioneers of AI started with, and their answer, well, it's the foundation for literally everything we're about to dive into. So if you're going to build a brain, where do you even start? Well, you'd probably look at the best example in the known universe, our own. The whole fundamental idea behind all this powerful modern AI isn't some crazy futuristic concept. Nope. It's actually directly inspired by biology. And boom, that's pretty much the whole game right there. See, the goal was never just to write a really clever piece of software. It was to create an artificial system that actually mimics how our own neurons connect, how they fire, and how they learn. It's less about building a super calculator and way more about growing a digital mind. All right, so if we're going to build a brain, we need the basic parts, right? The brain cells. Let's start at the absolute ground floor and look at the most fundamental component of our new artificial mind. Okay, say hello to the perceptron. This little thing is our artificial neuron. It's the simplest possible unit you can have, and you can think of it like a tiny, tiny decision maker. It just looks at a few pieces of information, and based on that, it makes a single, simple choice. Now, on its own, one of these isn't exactly a super genius, but trust me, it's the start of everything. And what it's really doing is super simple. It's basically taking a vote. The perceptron gets data, sure, but it doesn't treat every piece equally. It assigns a weight to each input, which is just a fancy way of saying it decides how important that piece of info is. After it tallies up all those weighted votes, it makes a simple yes or no decision. It's a simple process, but it's the foundation for all the amazing complexity that's about to come. Of course, a single neuron isn't going to get us very far. The real magic, the real thinking, starts when we connect thousands or even millions of them together into these organized layers. You've got the input layer, that's what the AI sees. You've got the output layer, which gives us the final answer. And all that stuff in between, those are the hidden layers. And that's where the heavy lifting, the complex thought, and the real pattern recognition happens. So how does one of these little neurons decide if it should pass a signal along to the next layer? That's the job of something called the activation function. You can think of it as the on switch. But here's the crucial part. This isn't just a simple on or off switch. It's what allows the entire network to learn the complex, messy, and totally unpredictable patterns of the real world, the things that aren't just a straight line. This is what gives our artificial brain its power. Okay, so we've built the structure. We've got our neurons, we've got our layers, but there's a problem. Right now, our brain is totally empty. It's a blank slate. It doesn't know a thing. So how do we teach it? How does it actually get smarter? The key is this incredible process called backpropagation. Now, that is a fancy, intimidating name for a really simple and beautiful idea. Learning from your mistakes. When the network makes a guess and gets it wrong, this algorithm goes all the way back through every single layer and tells each individual neuron, hey, here's how you contributed to that mistake. Then it just slightly tweaks their connections, those weights we talked about, to do just a little bit better next time. Now imagine doing that thousands or even millions of times. It gets smarter and smarter with every single pass. Now it turns out, just like with tools, you don't use a hammer for every single job. One type of brain isn't perfect for everything. Just like our own brains have specialized areas for things like vision and language, AI has evolved this whole toolkit of different brain designs or architectures, each one fine-tuned for a very specific task. First up, we've got the CNN. The easiest way to think about this one is as the AI's visual cortex. It's the part of the brain built specifically to understand images. It works by scanning for really simple things at first, like lines and curves and edges. Then, in the deeper layers, it starts combining those simple shapes to recognize more complex things, like objects, faces, and eventually entire scenes. And trust me, you use these things all day, every day. That face unlock on your phone, that's a CNN. When your social media app magically knows who's in a photo and suggests a tag. Yep, CNN again. And when a self-driving car spots a pedestrian in front of it, you guessed it, that's a CNN, hard at work, making sense of the visual world. Okay, next tool in our kit, the RNN. So if the CNN gives our AI eyes, the RNN gives it a memory. Its special trick is this thing called a feedback loop, which lets it remember what came just before the current moment. This is absolutely critical for understanding anything that happens in a sequence, like language, where the meaning of a word totally depends on the words that came right before it. This is the tech that powers things like your phone's autocomplete or basic language translation. Now, the first RNNs, well, they were a bit forgetful. They kind of had short-term memory loss. That's why you'll often hear about their souped-up cousin, the LSTM. It's just a better RNN with a much, much better long-term memory, which is vital for understanding long sentences, where the end might depend on something from the very beginning. All right, now for something completely different, and honestly, kind of mind-blowing. The GAN. This isn't just one AI brain, it's two of them, locked in an epic competition. They essentially play this game against each other, and in the process of trying to outsmart one another, they both become incredibly good at what they do. And this forger versus detective analogy is just perfect. You have the generator, that's the forger. Its only job is to create fake stuff, like a photorealistic image of a person who doesn't even exist. Then you have the discriminator, that's the detective. Its job is to spot the difference between the forger's work and a real photo. Every single time the detective catches a fake, the forger learns how to be a better artist. And every time the forger fools the detective learns how to be a better critic. This endless game pushes both of them to an unbelievably high level of skill. So let's just step back and look at our toolkit. It's pretty cool, right? We've got CNNs for seeing, we've got RNNs for remembering and understanding sequences, and we've got GANs for pure creation. Each one is this powerful, specialized tool designed for a specific job, and it's this kind of specialization that pushed AI forward for decades. But here's the thing. All of that amazing progress, it was all building up to something. In just the last handful of years, one particular architecture came along and just changed everything. It's responsible for the AI explosion that we're all living through right now. And this is it, the transformer. This is the powerhouse, the engine that's inside pretty much every large language model you've heard of, especially things like GPT. Its huge breakthrough was a totally new concept called an attention mechanism, and it fundamentally changed how a machine could understand language. So why was this such a total game changer? Well, think about how an RNN reads. It has to go one word at a time. It's sequential and slow. A transformer, it gets to look at the entire sentence all at once. That attention mechanism lets it figure out the relationships between all the words simultaneously, no matter how far apart they are. This unlocked two huge things. First, a much deeper, more nuanced understanding of context. And second, something called parallelization. Because it could see everything at once, we could suddenly train these models on a massive, unprecedented scale. That leap in both power and efficiency is what makes modern AI feel so incredibly fluent and, well, human-like. And that's our journey. Isn't that wild? We started with one tiny, simple idea, a single artificial neuron. We layered them, we taught them how to learn from their own mistakes, we developed all these specialized brain types, all the way up to these incredible models that can process and generate language in ways that are just astounding. We really did it. We built an artificial brain. So that leaves us with one big, final, and pretty profound thought. The technology is no longer the main barrier. We have these incredibly powerful minds now that can see, create, and communicate. The real question has shifted from can we build them to what should we do with them? What should we teach them next?
Thanks for watching.